Please check whether screen is visible to you, students.
Yes.
Yes, sir.
ओके, तो लास्ट टाइम हमने जो थियरम देखा था वो थियरम था नॉर्टन्स थियरम। फिर उसके बाद हमने देखा रेसिप्रोसिटी थ्योरम, उसके पहले थेवेनिन्स सुपरपोजिशन, मैक्सिमम पावर ट्रांसफर, दैट वी हैव कंप्लीटेड। टुडे वी आर गोइंग टू सी मिलमैन्स थ्योरम। Millman's theorem. You know, in Thevenin's theorem we reduce the circuit. Means ultimately जितने भी theorems है, that all are useful to reduce the complexity of the circuit. So the statement of Millman theorem is, if a circuit containing n number of voltage sources, n number of voltage sources, if I can say that V1, V2, V3 up to Vn, and their corresponding series impedances, I should denote it like Z1, Z2, Z3 up to Zn respectively, and those are in parallel. Then these sources means this all V1, V2, Vn can be replaced by a single voltage source, of voltage Vm, M is taken for Millman's theorem, having a series impedance, Zm, where Vm and Zm are given by I'm just writing those equations. Vm equal to V1 Y1 plus V2 Y2 plus Vn Yn upon Y1 plus Y2 plus up to Yn. Since Yn are, you can say those are conductance, okay, that 1 upon Z equal to Y. So I can just simplify this equation like summation starting from k equal to 1 to n of the product of Vk and Yk divide by summation starting from k equal to 1 to n Yk. So this can be solved, that Vm can be solved using this equation, and this Zm, equation of Zm, that you can find out like 1 upon y1 plus y2 plus yn. So that can be written as 1 upon summation k starting from 1 to n yk, where y1, y2 up to yn are known as admittance and z1, z2 all are impedance. Okay, so we'll see one example based on this one. So here what is written, you see in the statement it is written that if a circuit containing n number of voltage source V1, V2 up to Vn and that their corresponding series impedance Z1, Z2 up to Zn, and those need to be parallel. So we can convert this all sources and impedances in a single source and a single series resistance Zm. So single source we are going to convert, that is Vm, and single impedance, that is Zm. So the equation of that Vm and Zm is given. So how to convert that? Let us take one example based on that. Convert the given network into single source and impedance using Millman's theorem. Okay, so I am going to draw that network, then after we'll convert that, or we can reduce that network using the Millman theorem. I should write like this way, that this network need to be reduced across AB terminal. Okay, so I'm not using this one. So our AB terminals are this one and this one. Let me just reduce this one, so you can write, we'll get more space to write. This is A terminal and this is B terminal. So using Millman theorems across A and B terminal. Okay. So this is positive terminal, this is negative terminal. Now I'm drawing those elements. So here is one series impedance. Suppose this is a Z1. The value is 1 ohm. Here is one voltage source, that is independent voltage source. Suppose this is a V1 and the value is 2 volt DC. Here one more impedance, or you can say resistance, that is Z2. Here one more voltage source, plus minus. The value is 2 ohm, and for this is a 3 volt voltage source. This side one more impedance, that is Z3. The value is 2 ohm, and this value is 5 volt. This is V2 and this is V3. We need to convert this network. See, as per Millman's theorem, and this one, you see, this is V1, V2, V3. All voltage sources are in parallel. Along with this Z1, Z2, Z3 are series with each and every voltage source respectively. And that combination, this full network can be replaced by VM and ZM. So that circuit we are going to replace with single voltage source and single impedance across AB terminal. So here will be A and B terminal, and over here this is converted to VM, and this one will be ZM. So here is, we'll convert that as per Millman's theorem. This will be VM and this will be ZM. So we have seen the equation of Millman's theorem, that VM we need to find first VM. So VM equal to, see over here 3 voltages are there and 3 impedance. So we can write like this way: V1 Y1 plus V2 Y2 plus V3 Y3 divided by Y1 plus Y2 plus Y3. So in our case, V1 is 2 volt, V3 is 3 volt, and V2 is 3 volt, and V3 is 5 volt. So you put each and every value in this equation, we will get this V1 is how much? It is 2. Y1 will be 1 upon 1 plus, you see, Y1 equal to 1 upon Z1. Okay, that is admittance. So we are writing like that way. V2 is 3 and multiplier Y2 is 1 upon 2 plus V3 is 5 multiply 1 upon 2, that is Z3. Y3 is 1 upon 2. So here will be 1 upon 1 plus 1 upon 2 plus 1 upon 2. Just quickly simplify this one and give me the answer quickly. What you are going to get? VM. Just simplify this one and give me the answer.
3, sir.
3 volt. 3 volt. Okay. When you simplify that, you are going to get this 3 volt. And for Zm, when you do the calculation for Zm, equal to 1 upon Ym. So here is nothing but Y1 plus Y2 plus Y3, that is equal to 1 upon 1 by 1 plus 1 by 2 plus 1 by 2. What you are getting in this one?
0.1.
0.5, right? 0.5 ohm. So this will be 0.5 ohm. So this is what our converted circuit or converted network as per Millman's theorem. This is the complex network. We have converted, or we have reduced the complexity and converted it to single impedance and single voltage source as per the Millman's theorem. Anyone having any doubt in this one?
No, sir.
Okay.
No, sir.
Now based on this one only, we are going to see one more example. Calculate the current I. Calculate the current I shown in the diagram or shown in the network. Using Millman's theorem. I'm going to draw that network. We need to find the value of I in this given network using Millman's theorem. So here are the elements. This side one source is there, that is plus minus 10 volt source. Here is 2 ohm resistor. This side one more resistor, it is 3 ohm resistor. Current passing through 3 ohm, that is I. Here is one more resistor and the value is 5 ohm. And this side one more source, the value is 20 volt. So we need to find a value of I, current flowing through this 3 ohm resistor using Millman theorem. So you see in this network, this branch and this branch both are connected in parallel. So I can draw like this way, this network. I'm just shifting this one this side. So over here, this is the first branch, it's the second branch, and over here this 3 ohm. So this is what a 2 ohm. I'm just simplifying this network, modifying this network for understanding only. So modification is not done like I have connected other branch in some other branch. Just simplified this network for understanding. It's 20 volt. This is a 5 ohm. So these two parallel network at this junction, you see from this junction, all three branches are in parallel. So this is what the same junction over here. And this is what my 3 ohm resistor and current flowing through that, that is I. So I want the to get this current I, suppose this is terminal A, this is terminal B. So I want to convert this branch. I'm going to convert these two branches, this one and this one, to single resistor, because this both are parallel with each other and this both sources are parallel with each other. So I can use like this is my V1, this is my V2, and this is my Z1 and this is my Z2. So you use this equation Vm equal to V1 Y1 plus V2 Y2 upon Y1 plus Y2. See, you see here, this is a 10, that V1 is 10, V2 is 1 by 2, Y2 is 1 by 2 plus this V2 is 20 and Y2 is 1 by 5. Then after Y1 is 1 by 2 plus Y2 is 1 by 5. Just do the simplification and tell me the answer quickly. Vm is what you are getting. Quickly do the simplification and tell me the answer. What you are getting?
12.8 volt.
12.8
12.8.
12.85.
So 12.8 volt. 1.8.
12.85 volt. Okay, so this is what our VM. We'll convert that network into single, and then after we'll solve it out. And now the remaining one, that is Zm. Zm equal to 1 upon 1 by 2 plus 1 by 5. Just tell me this one.
So 1.428.
1.428 ohm. Okay, so this is what we are getting. Now we just convert this one. See, across AB terminal, we are converting this network as per Millman's theorem. Then after we'll get the value of I. So this is single source and single impedance, and this is one resistor. So this is what we have got, that is Zm 1.428 ohm, and this is what Vm, this is Zm, this is Vm is 12.85 volt. This is Vm, we have already derived. Over here it is 3 ohm, and current flowing through that is I. This is a terminal and this is a B terminal. Now apply KVL, because you see this is the loop where current flowing I in the loop. What you can say, I equal to series impedance is that V by R, so 12.85 upon total R is 1.428 plus 3, because it is in series, so V by R form. Do the calculation and tell me the answer. Quickly do the calculation and tell me
Sir,
the
it's 2.9.
2.9.
It's 2.9 ohm. I'm ohm.
2.9 ampere. Okay, you are getting 2.9 ampere. So this is the correct answer. Any doubt, anyone?
No, sir.
No, sir.
No, sir.
No, sir.
Okay. So we are going to see last theorem of this unit, that is known as substitution theorem or substitutional theorem. Substitution theorem. So I'm writing the statement of this substitution theorem. So substitution theorem states that the voltage across any branch, the voltage across any branch or the current through that branch or a network, being known, the branch can be, means whatever branch we are talking about, like a specific voltage across that branch or current through that branch. So that branch, the branch can be replaced by, can be replaced by the combination of various elements that will make the same voltage, that will make the same voltage and current through that branch, So here what it is exactly said means, suppose we are considering one network where we'll take one branch. See, such branch where in that voltage drop across that branch or current flowing through that branch, we can replace that branch using various elements, and after replacing the elements means the property like a voltage drop or you can say a current through that branch should not be changed. Suppose if I say one example based on this, suppose I am taking one network, sorry, one loop, single loop I am going to consider. This one, suppose one source is there and two resistors are there. We draw that. Suppose this is a independent voltage source of 10 volt. Here is one resistor, that is, suppose this is a R1. This is suppose if I say this is a 5 ohm, and suppose this is a R2, and suppose this is, I'm getting 10 ohm, I'm writing 10 ohm here. Now I want to replace this branch using substitution theorem. Suppose this is AB branch. Using substitution theorem, I want to replace that, and I'm going to draw a new network, but its property should not be changed. Like I'm going to replace this with other elements. I'm going to replace this branch with other elements. So before replacing this, I need to know the voltage across these two terminals. Ultimately, voltage across this R2. So how I will get the voltage across R2? I need to know the current from this, because the current is I. If I say the current is I flowing through this way, so if I find the value of I equal to V by R, so 5 plus 10, sorry, that V by R is 10 divided by 5 plus 10, so that is 10 divided by 15. This is what ampere we are getting. So these two terminal, if I say this is a plus 1, this is a minus 1, and if I want the value of this VR2, so VR2 equal to the resistance R2 into I. So R2 is how much? That is 10 multiplied 10 divided by 15 current. So 100 divided by 15. So that is a voltage drop across this R2. I can replace this branch using some other elements. But the thing is, voltage drop across AB, this voltage across AB should not be changed. That VAB should not be changed, and the current I should not be changed. Then and then I can do that. So 100 by 15, if you do this, do that 100 by 15, how much you are getting?
6.66.
6.66. 6.66 volt. Okay. Now I want to replace this. So just I'm taking this one on new page. I want to replace this one. I'm drawing a new network with a replacement. So this one is the network, but across AB I'm going to draw some other element and I'll check the property of the same. I want to change over here only. So this is what a 10-volt source. Over here is R1, that is of 5 ohm. This is my terminal A, this is my terminal B. I'm just connecting over here 6.66 volt source. Now you see, this is where if I going to measure over here across this AB branch, I will get the value 6.66. Okay, but whether the branch current is I is like whatever current flowing through this branch in this loop, suppose if I say this is I, is it satisfying the I value which is over here, this one? That is what we need to check. So what we'll do, in suppose this is network A, in this is network B. In network B we find, so this is I1 now, I1, so I1 equal to, we see you apply KVL to find that. So let us apply KVL first. Apply KVL. How you will get? You see, this is plus 10. You move from this side, plus 10. Then after over here, minus 5 into I1. See, this is I1. Minus 6.66 equal to 0. Now try to find this one. You can find that 10 minus 6.66 equal to 5I1. Now try to find this I1, what you are getting. Simplify this one and tell me the answer. What you are getting?
0.668.
3 point, sorry,
0.668. 0.668.
5. So 0.668 ampere, correct? Now we had the value of I. This is what the value of I. Now when you divide these, what you are getting? 0.66 over here. This is what ampere. And when you compare these, you see, when you compare this, I equal to I1. So both the value are same. You got the voltage drop even equal. So your circuit is satisfying the condition after replacement. This is what substitution of branch AB. Now one more network, I'll try to substitute this branch once again. I'll use another element to replace this. So let us go with this one. I'm using the same network A and I'm going to develop a network C. So now over here, I'm drawing another network. If you are getting any doubt, you just let me know, okay? So over here, I'm not going to change any of the branch other than AB, okay? So this is the same 10 volt. This is the same R1 5 ohm. This branch A, B. I'm just changing this one with this current 0.666 ampere current source. Now I need to verify the voltage across this AB terminal. This is plus terminal, this is minus terminal. Because you see, I have connected this current 0.66, this current source. So the current flowing this I is nothing but 0.66 ampere. Okay, but I don't know the voltage drop across this. So that V plus minus, that I need to know. Okay, this V plus minus I need to know. So suppose this is a network C. Apply KVL to find this V. So when you apply that, you can find that find V in network C. Okay, so when you apply that, you can write 10 minus 5 into I is nothing but 0.666 ampere minus V equal to 0. Try to find that. What you are getting? V equal to 10 minus 5 into 0.666. What you are getting? Give me the answer quickly.
6.67.
6.67.
67 volt. Okay, 6.67 volt. And that is what you can compare with the last example, like whatever VR2 we have found out. VR2, if you check the VR2 equal to VAB, and that is what we have got, 6.66 volt. And you can compare, that is nothing but V we are getting in network C. Is it all right?
Yes, sir.
Yes, sir.
Yes, sir.
Likewise, if I go further, if I still go further for the same network, let me take this third one. I want to replace this AB branch by substitution theorem with some other elements. I cannot change the current flowing through that branch. I cannot change the voltage drop across that branch. I am considering AB branch. Now I am just changing the elements. This is 10 volt as it is. This is what a resistor R1, 5 ohm. Current flowing through that is I. I'm just changing like this way. Now you see some R2 resistor I'm using over here. So I want to find this voltage V and voltage then resistor R2 value, so that this VAB should be 0.66, like 6.66 volt. It should be like that only. So you can take like this way. Suppose you are considering this one plus minus, and you consider this I into R2. So we already know, suppose we want to make it like we want to make this voltage drop is 6.66 actually. Suppose I am just taking 1.66. I'm just taking from here 1.66 voltage drop, and remaining 5, like I am making it like 1.66 plus 5, like this way. I'm making a combination of this one. So 1.66 equal to I cross R2. So I'm having the value of I, that is nothing but 0.666. So R2 I can make is 1.66 divided by 0.66. So I have already taken this one as a 5, and remaining I am just adjusting over here. So this 5 I have taken as a source, and that is what over here I want to make this one R2. So tell me this one 1.66 divided by 0.66. What you are getting over here?
2.492.
How much?
2.492.
4.2
2.
sorry.
Yes.
2.492.
492. Yes, sir.
This is what we have to use like variable register because this is not a standard value. 2.492 ohm. Okay, you can cross check this. You can cross check this, and you can find the voltage across AB even you can find the value of I in this one, and that will be, you will find that voltage across VAB over here, you will find that 6.66 and I will be 0.666 ampere. You can cross check this and you can verify this. So this is our various method you can apply using substitution theorem, and you will able to understand how that substitution theorem helps to convert the network branches in other using the other element. But the thing is, you cannot alter the value of I, you cannot change the voltage drop across that branch. Okay, understood? Or any doubt, anybody? Students, any doubt?
No, sir.
No, sir.
Okay, you can modify this up to you. Okay, you can modify, like suppose I have taken 1.66 plus 5, you can take 2.66 plus 4, 3.66 plus 3, like that way also you can take. Okay, so
Sir.
yes,
No, sir, nothing.
okay, so I'm just stopping over here, and this chapter is done, this topic is done. Now from next time onwards we are going to see a new unit, that is time domain analysis and a frequency domain analysis of network, and that we are going to see on Wednesday. I'm stopping over here.